Welcome back to All This Math. This is Professor Parker, and for this lesson, we're going to get into some probability tree diagrams. Probability tree diagrams. We're going to go over a word problem. Now, you can see the word problem is not written on this board, but the word problem is in the description below this video, all right? Or it's in the description on this page. Make sure you're subscribed to the All This Math YouTube channel. We also have content on Instagram. So subscribe, or not subscribe, but follow us on Instagram as well for content over there too. I'm wearing one of my favorite sweatshirts. This is my Asada is Welcome Here sweatshirt. This is referring to Asada Shakur. All right, and if you're familiar with this channel, you know that this poster is up here, been up here for a while. This is a picture of Asada Shakur, probably from about maybe 30 years ago, maybe. I'm not sure what the date on that is. I got a couple of books on here, books out here. Of course, her autobiography. This is a classic. Go grab this, read this. All right, Asada by Asada Shakur. All right, and then there's another book I got put on to by the good brother Marcus Klein out in Chicago at Freedom Home Academy. Check out some of the work he's doing at his independent school. This is called Inadmissible Evidence. This documents some of the work that her aunt did, Asada Shakur's aunt, who was an attorney, in terms of defending the Black Liberation Army, of which Asada Shakur was a member of at one point. All right, so a couple of books you should check out: Asada, and also Inadmissible Evidence by Evelyn Williams. All right, so let's get into this problem. So probability tree diagrams. This is how the problem goes. It says this, right? A bag. So imagine a bag, right? A bag has 5 red marbles and 10 blue marbles. All right. Now, whenever I see these probability questions that deal with marbles, I always be thinking of that Martin episode when he came back from the cult and he was Brother Shaquille Sunflower. And then he came back home and Gina had packed up all his stuff and put it in boxes and got rid of a lot of his stuff. And he was like, where my marbles at? Where my marbles at? Right? I always be thinking about that, right? Whenever I see one of these problems, I don't know, my mind just be going there. But anyway, I just want to say that because it was in my head. Because like I said, whenever I see a problem with marbles in it, I be thinking about that. But anyway, a bag has 5 red marbles and 10 blue marbles, right? Ruqayah selects 2 marbles without replacement. So that without replacement thing I just said is very important. Some of these probability problems deal with replacement, meaning you take the marble out, put it back in the bag, all right, before you take out the next marble. Some of the problems, you take the marble out and you leave it out, all right, and then you take another marble out. That affects the probability. That affects the calculation of the probability because you have a different amount of marbles left in the bag when there's no replacement. All right, so we're going to answer 2 questions. Question 1, what is the probability of selecting 2 red marbles on the two pulls, right? Question 2, what is the probability of selecting a red marble first and then a blue marble, right? Or not necessarily in that order, but a red marble and a blue marble. What's the probability of that? So we're going to draw a probability tree. All right, so this how this goes down, right? You draw the probability tree, right? Then what I like to do is I like to create a column for the outcomes, the potential outcomes, right? Based on the information in the probability tree. And then after the outcome column, then I have a column for probability, which shows the calculation of the actual probability for each of the outcomes. All right. So let's get to drawing. Let's start drawing the probability tree. All right. So I'm going to use a black marker. And so we got red marbles and blue marbles. Throw my clipboard on the floor. All right. So we start out here. Let me start right there. Draw 1 branch, 2 branches like that. All right. So we got red marbles and blue marbles. So let's use the letter R to represent the red marble. Let's use the letter B to represent the blue marble. So I put the R right here because that symbolizes pulling out a red marble. I'm going to put a letter B right here because that symbolizes pulling out a blue marble. All right. Now, that's the first marble. That's the first time I pull a marble out. This is what happens. Either one of 2 things can happen. Either you're going to pull out a red marble or you're going to pull out a blue marble. Notice the problem didn't say nothing about green marbles, orange marbles, yellow marbles, black marbles, white marbles, clear marbles. It ain't say nothing about that. It just said red marbles and blue marbles. So we keeping it simple. You only got two choices. So that's why you got two branches, because you got two choices. Two branches, two choices. Two choices, two branches. Now, if I repeat something in these videos, that should be a hint that you need to make sure you have it written down in your notes. As you watch these videos, you should be taking notes. So I'm also trying to teach you note-taking skills, because a lot of people think, well, it's math class, I don't got to take notes. All you got to do is copy down the problems. That's wrong. You do need to take notes. In a math class, you definitely need to take notes. All the different ad-libs that your teacher might have, the different little steps that they give you, you got to figure out what to write down. You got to write that stuff down. Don't just be that person sitting in class just copying down the problem and you have no idea why the steps are happening the way they are. Write down a narrative so you can tell a story to yourself in your notes of what you're doing from step 1 to step 2. Step 1 is draw two branches. At the end, put symbols to represent each of the outcomes. Red marble, blue marble. Now, Ruqayah, because that's the person in this problem, right? Ruqayah pulls another marble out. All right? So watch this. Boom, boom. So after she pulled, like, let's say if she pulled out a red marble, then she pulled out another one, she still got two choices. She could pull out another red one or a blue one. All right? But what if she had pulled out a blue one? If she had pulled out a blue one, and then she pulls out another one, she still got two choices again. She could pull out a red one or a blue one. All right? Now, she's only pulling out two marbles, right? She's not pulling out 3. She's not pulling out 4. She's not pulling out 5. She's only pulling out two marbles. So therefore, you got your first pull, right, is this branch. Then the second pull represents these two branches, or these 4 branches rather, right? So 2 branches, 4 branches, all right? First pull, second pull. First pull, second pull. First pull, second pull. All right? Now, your outcomes. Outcomes, and then next to that, we're going to have probability. Probability. Yeah, I spelled that right. Cool. All right, so these are your outcomes. So at the end of this branch, this represents going from red to red. So pulling out a red marble, then pulling out another red marble. So that outcome, we're going to call that RR. All right. The end of this branch, this represents pulling out a red, then pulling out a blue. So we're going to call that RB. And we're going to get through this problem kind of quick, I think. At the end of this branch, this represents pulling out a blue first, then a red. So that's BR. So we have RB, now we got BR. All right. Now, at the end of this branch, this outcome, end of the branch, outcome, represents pulling out a blue marble, then another blue marble. So we got B, B. That's what we're going to call it. So we got our 4 outcomes. All right, 4 outcomes. So at the end of this, each of the branches of the tree diagram, that's where you get the outcomes from. You get the outcomes from the ends of the tree branches, the ends of your tree branches. So the end of this branch is right here, but how did we get there? We went from R, we started here, went to R, and then went to R. So that's RR. How did we get here? Went to R and then to B. That's RB. How did we get here? We went to B, then we went to R. That's BR. How did we get here? We went to B, then to B. That's BB. So those are 4 possible outcomes. We only got 4. We don't got 5. We don't got 6. We don't got 7. We got more than 3. We got more than 2. We got exactly 4. And you can see where the 4 comes from. That's why that's the beauty of the tree diagram. The beauty of the tree diagram is you can get a visual representation of what's going on. All right? Now, probability. Now, before we calculate probability, what I want to do is go back in here on the tree diagram and show the individual probability. All right? Now, make sure you got to pay a little attention here, right? Because the original problem said that there were 5 red marbles and there were 10 blue marbles. 5 red marbles and 10 blue. All right? So that means that's going to, in a probability, a probability can be represented by a fraction or a percentage or a decimal. But we start out with a fraction usually, right? I'm going to start out with a fraction. The denominator is the total amount of things. So in this case, it's the total amount of marbles. That's your denominator. Remember that. Write that down. Your denominator is the total amount of things. Your numerator, because a fraction got 2 parts, right? It's got a numerator on top. It's got a denominator on the bottom, right? That's why you learned how to deal with fractions. So when you get older to the grade you're in now, or the level you're at now, you can do probability using fractions, right? The numerator is the number of the thing that you're focused on. So if I'm focused on what's the probability of pulling out a red marble, then I'm focused on the number of red marbles in the bag. All right. My denominator is the total number of marbles. My numerator is only the number of red marbles if I'm focused on what's the probability of pulling a red marble. So in this case, since it's 5 red marbles in a bag and it's 15 marbles altogether, the probability is 5/15. So it's a 5 out of 15 chance I'm going to pull a red marble. All right. Now, what about the chances of pulling a second red marble? Now, this is where you got to read and pay attention. When we're doing word problems, you got to read and pay attention, right? Because this particular word problem said there's no replacement. There's no replacement. In some word problems, they deal with, there is replacement, meaning you put the marble back in the bag after you pull it out. In some word problems, you don't put the marble back in the bag after you pull it out. That's something you really got to pay attention to. Is there replacement or is there not replacement? Is there replacement? Is there not replacement? In this problem, there's no replacement. So that means that there used to be 15 marbles. Now it's only 14 marbles because it's one less marble because there's no replacement. Also, if this were to happen, that means it wouldn't be 5 red marbles. Now it's only 4 red marbles. So that means that our probability of pulling out a second red marble is going to be 4 out of 14. 4 out of 14. 4 out of 14. So that's why you write. That's where you write it. 4 out of 14. Now, just in case you don't understand it, let me go over that again. Why is it 4 out of 14? Because that first red marble that got pulled out, if it got pulled out, because this is based on this thing actually happening, right? So if the first red marble gets pulled out, now it's not 15 marbles in the whole bag no more. It's not. It's one less. 15 minus 1 is 14. It's only 14 marbles left altogether, red and blue altogether. And if one of the red marbles got took out, it's not 5 no more. It's only 4 left. So that's how you get 4 out of 14. Now you might be wondering like, oh, why ain't we reduce the fractions? We can deal with that later. For now, I keep the unreduced fractions in our probability. So 5 out of 15 for the first red marble, 4 out of 14 for the second red marble. Now, what about the probability of this blue marble on the second pull? The blue marble on the second pull. Blue marble, but on the second pull though. Again, one of the marbles didn't get replaced. So our denominator is still going to be 14. And this is based on the first marble being pulled being a red one, right? We didn't pull a blue one. So originally there were 10 blue marbles, right? So it's still 10 blue marbles. It's still a chance to 10 out of 14 of pulling a blue marble, because in this scenario on this branch, this means we pulled a red marble first. All right. So pulling a red marble first don't got nothing to do with the amount of blue marbles that's still left in the bag. If you started out with 10 marbles, it's still 10 marbles in there. They're still there because you didn't pull a blue marble out yet. All right, now let's go down here to this branch. So first pull, what's the probability of pulling a blue marble? Because it's 15 marbles altogether, because we're starting over again. This is starting over again, right? The first branch, right? Just like up here. It's 15 marbles altogether, so that's my denominator. And how many blue marbles? We start out with 10. So we got 10 out of 15, right? Now let's say we go from the blue marble to the red marble. Blue marble to the red marble. Now, because there's no replacement, again, our denominator is going to be 14 now, not 15. It's going to be 14 because we didn't replace that one that we pulled out, right? But how many red marbles are there based on this branch? Based on this branch, we started out with 5 red marbles, right? It's still 5 red marbles because based on going this way, pulling a blue marble out first, you ain't pulling no red marbles out yet. You pulled a blue marble out first. So if you pulled a blue marble out first, you didn't touch none of the red marbles. So if you start out with 5 red marbles in the bag, it's still 5 red marbles in the bag, even though on the second pull, right? Because it's not like this scenario. In this scenario, you start out with 15 marbles altogether. It's 5 red marbles altogether. Then if you pull one out and don't put it back, now it's only 4 red left, right? And 14 marbles altogether. But here, if you pull out a blue one first, you still got 5 red marbles in it. So keep that in mind. All right, now, what about this branch right here? What about this branch? So if we start out with, we pull out a blue marble, then we pull out another blue marble, our denominator is still going to be 14 because there's no replacement. Again, I keep reinforcing that. There's no replacement, right? Now, If it was 10 blue marbles and I pull one out, right, and I don't put it back, again, no replacement, it's only 9 blue marbles left. So this is the probability of pulling out a second blue marble, 9 out of 14. The probability of pulling out a red marble on your second pull is 5 out of 14. And so on and so forth. You see how all these numbers are different? That's why you got to really pay attention to these type of problems, because if there's replacement, it's a little easier because the probability is not going to change. If there's no replacement, then it's a little more, you got to think a little more. You got to pay attention. But it's not difficult. You just got to pay attention. All right, so now, for our probability over here, our probability, right? I want to know what's the probability of this outcome. A red, then another red. A red marble, then another red marble. Basically, a red marble and a red marble. Notice how I use the word and. I'm being very intentional by using the word and. Because in probability problems, the word and means multiply. Math is a language. Math is a language. If we think of it as a language and we try to learn it as a language, then it probably would become a lot easier to us. There are certain words in the English language, right, that could be translated to certain operations and actions in mathematics. In the context of probability, though, the word and means multiply, whereas usually in most math word problems, the word and means addition. But that involves context. And that's something that we deal with all the time. Just like, like the phrase, like in English language or like in the vernacular, among our people, if you ask somebody, you say, you good? That could mean a lot of things, a lot of different things based on the scenario, based on the situation. Asking somebody if they good, like you might actually be showing compassion, empathy, concern for them, for their well-being, right? Or you might be, trying to let them know like, yo, don't come over here with no nonsense or it's going to be a problem, right? It depends on the context, right? So just like the word and in math, if we're doing probability problems, in this context, that means multiply. In other contexts in math, it means do addition. All right? So keep that in mind. Now, so basically we take the probability of pulling out a red marble first, which is 5/15. And we're going to multiply that. See, I use a dot for multiplication. That's my favorite symbol for multiplication, the dot. You can use an X, use parentheses, asterisks, but I prefer the dot. And then the second outcome is another red marble, which is 4/14. All right, so 5/15 times 4/15. I can't cross cancel because these diagonals don't have a common factor except for 1. So I'm going to just horizontally multiply. 5 times 4 is 20, and 15 times 14. I know this is how I do this mentally, right? Again, there's a lot of cheat codes in math, right? This is 15 times 14. I don't know that off the top of my head. I should have it memorized, but I don't, all right? That's one of my goals, to memorize the higher multiplication facts, right? But I do know 14 times 14. I know my perfect squares, right? Up to a certain point. But I know 14 times 14 is 196, right? So 14 14s is 196. 15 of them means just one more 14. So if I know 14 times 14 is 196, this is a trick that you can use too. I just add another 14 on top of that. Because remember, multiplication is just repeated addition. What this can be thought of is adding 14 15 times, or putting 15 14s together. 14 plus 14 plus 14 plus 14 plus 14. That's really all that is. So I could do 196 plus 14. 196 plus 14 is 210. Because 196 plus the 4 is 200. And then plus the other 10 is 210. So this is 20 over 210. Oh, but you know what? See, I couldn't cross cancel, but I could have just reduced this. Actually, I could have reduced both of these. I wasn't even paying attention. I said something about it earlier, but I could have reduced both of these, and then it would have made the multiplication easier. But anyway, I could do it now. So now I got 20 over 210. These zeros can cancel out, leaving me with 2 out of 21. So 2 out of 21 is the probability of this happening. 2 out of 21 is a 2 out of 21 chance that this outcome will happen, that you will pull 2 red marbles back to back without replacement. All right. Now, what's the probability of this outcome? First, the probability of pulling out a red marble is 5/15, right? And the probability of pulling out a blue marble is 10/14. See, I keep using the word and, that means multiply, just like in this one. Now, well, actually, with this one, I could cross cancel. So the 10 and the 15 can cross cancel because they have a common factor of 5. So 10 divided by 5 is going to be 2. 15 divided by 5 is going to be 3, right? And then I got 5 over 3 and 2 over 14. 2 over 14 I can reduce, right? So 2 over 14, 2 divided by 2 is 1. The common factor is 2 because they're both even numbers. 2 divided by 2 is 1. 14 divided by 2 is 7. So now I got 5 over 3 times 1 over 7. So 5 times 1 is 5. And 3 times 7 is 21. So that means there's a 5 out of 21 chance that this outcome can happen. 5 out of 21 chance that this outcome can happen. All right? Now, what about this outcome? A blue marble, then a red marble. Blue marble, then a red marble. Now, the blue marble is 10/15. The red marble is 5/14. A 5/14 chance that's going to happen. All right? Now, what can I do? What can I do? Oh, I'm cross-canceling all day on this one. So 15 and 5 have a common factor of 5, right? So you're going to divide each one by 5. And 5 is the greatest common factor. So you're going to divide 5 by 5 to get 1. You're going to divide 15 by 5 to get 3. Then we cross-cancel with the 10 and the 14. So the 10 and the 14 have a common factor of 2. So you're going to divide each number by 2. 10 divided by 2, 14 divided by 2. 10 divided by 2, 14 divided by 2. We're cross-canceling. It's called cross-canceling because you work in a diagonal direction. All right, so 10 divided by 2 is 5. 14 divided by 2 is 7. And then you multiply horizontally. 5 times 1 is 5. And 3 times 7 is 21. You'll notice that the probability is the same because it's really the same outcome, even though it happens in a different order, right? Because if it's happening in a different order, it's actually a different outcome, right? Because of the order, because the order matters, right? The order matters. But it's the same, technically it's the same outcome, but it happens in a different order. So we treat it differently. All right, now, what's the probability of pulling out 2 blue marbles, right? So 2 blue marbles. So the probability of pulling out a blue marble first is 10/15. The probability of pulling out a blue marble second is 9/14. So we're going to multiply them together. Let's see if we can cross cancel. Yep, we can cross cancel. 9 and 15 have a greatest common factor of 3. So we divide each of these by 3. Now, the reason that I'm so quick with this is because I know my multiplication facts. So do yourself a favor. Learn your multiplication facts. Know how to do 1 times 1 up to 12 times 12 at a minimum off the top of the dome. Off the top of the dome. You should be as fluent with your multiplication facts as you are with recognizing your family members. Like if you see your brother walking down the block, you see your sister walking down the block. As soon as you see them, oh, that's my brother. Oh, that's my sister. You should be just as fluent in that way as you are with multiplication facts. As soon as you hear somebody say, or as soon as you see on the board 6 times 9, you should automatically know, oh, 54. With no thought about it. You got to get yourself to that level. You got to practice. So if you, whatever grade you in, whatever age you are, whatever level you at, if you don't know your multiplication facts, do yourself a favor. Go learn them. It's never too late. Go learn them. Multiplication facts. Memorize them. Have them memorized. At a minimum, go up to 12 times 12. Know all your facts, all your 1 facts, 2 facts, 3 facts, 4 facts. And also, it's really not as many as you think about because let's say you memorize 4 times 5. Once you know 4 times 5, because of the commutative property, you automatically know 5 times 4. Because in multiplication, the order don't matter. 4 times 5 is the same thing as 5 times 4. And think of how many examples it is like that. If you know 7 times 3 is 21, then you automatically know 3 times 7 is 21. So every time you memorize, with most of the facts, every time you memorize one of them, you're automatically memorizing another one at the same time. 11 times 3, that's 3 times 11. Right? They're both within that group of facts, right? Both of those 2 statements I just said, 11 times 3, 3 times 11. So that's another thing. So don't get overwhelmed and be like, oh, it's too many. It's too many to memorize. It's really not that many for real. But memorize them. Do yourself a favor. Because then you could do stuff like the different cheat codes in math. You could do cross-canceling. You could reduce fractions. You could simplify fractions. You could do all of that. But you got to memorize your multiplication facts. Ain't no way around it. Just go memorize them. Right? You're going to need to do it. So anyway, the common factor and again, if you know your multiplication facts, then you're going to know all the factors of all the numbers easily because you're going to know what numbers multiply together to make what. You're going to know that because you know the multiplication facts. And then once you know the multiplication facts, you're going to know your division facts. See, everything is connected. Everything is connected. I'm trying to tell you. All right. So anyway, greatest common factor of 9 and 15 is 3. 9 divided by 3 is 3. 15 divided by 3 is 5. This diagonal, 10 and 14. Greatest common factor of 10 and 14 is 2. They both even numbers, so the greatest common factor is 2. 10 divided by 2 is going to give me 5. 14 divided by 2 is going to give me 7. Now, 3 over 7 I can't reduce, but 5 over 5, what can I do with that? Cancel them out. Anytime you have a fraction with the same numerator and denominator, that whole fraction is equivalent to just 1. And 1 over 1 is the same thing as 1. So then we multiply, and we got 3/7. Now, one of the ways we can kind of check our work is to add up all the probabilities and make sure that all the probabilities add up to 1, to a value of 1. So 2 over 2 21st plus 5 21st plus 5 21st plus 3/7 should equal 1. Now let's see. Now these all have a denominator of 21. I'm going to change this so it'll have a denominator of 21. I'm going to make it 9 over 21. Now, how did I know how to do that? Because I know my multiplication facts. Because if I want a denominator of 21, I need an equivalent fraction that has a denominator of 21. I need a fraction that has the same value as 3/7, but it also has, see, it's like a puzzle, but it also has a denominator of 21. So I change the denominator to 21 and I say, well, how did I do that? I did 7 times 3 to get 21 in my denominator. So as I do below, I got to do above. Whatever I do on the bottom, I got to do on the top. So if I do 7 times 3 to get 21, then that means I also got to do 3 times 3, and that gives me 9. See, I know my multiplication facts, so I can do that. So now I add them all up. 2 and 5 is 7. 7 and 5 is 12. 12 plus 9 is 21. So they all add up to 21 21st. All right. So that's kind of a way to check your work. So now, since we know all the probabilities of all the potential outcomes, right? Now we go back to the problem and we say, okay, well, what are you asking us now? Now, the first question was, what is the probability that Ruqayah is going to select 2 red marbles? All right. So there's only one outcome like that. 2 red marbles. Is this one right here. 2 over 21. So A, well, this is actually not number 1, it's number A. It's 2 over 21. Now, if I wanted to convert that to a percentage, because a lot of times we deal with percentages when we're dealing with probability, this would be 9.5%. Now, how will we get that? You do 2 divided by 21, it gives you a decimal. That's going to be 0.095. No, it's going to be 0.095. Actually, it is. Is it? Am I tripping? Yeah, it's going to be 0.095. 0.095, then we multiply that by 100. It gives us 9.5. Now, see, you got me. I'm sitting there questioning myself. I shouldn't be questioning myself. That ain't good. Yeah, I know I was right. I knew what I was talking about. Yeah. That number just seemed a little small for some reason. A little too small. But yeah, so there's a 9.5% chance that this could happen. It's kind of slim. Almost 10%. So there's only a 10% chance you're going to pull 2 red marbles. All right, so that's the first question. The second question was, what is the probability of selecting a red and a blue? A red and a blue. So a red and a blue would be these 2 scenarios. Actually, I shouldn't say red and a blue. Well, actually, I do mean to say red and blue, but it's 2 different scenarios. So that means I'm trying to find out what is the probability of either this happening or that happening. And notice how I'm trying to really enunciate the word or, because in probability problems, the word or means you do addition. Or means you do addition, right? The word and means that you multiply. The word or means you do addition. So this or that, this or that, this or that. So this is 5 over 21 plus 5 over 21. They add up to 10 over 21. So the probability of pulling a red marble and then a blue marble, or a red marble and a blue marble, is going to be these two put together. 10 out of 21. Which as a percentage is 10 divided by 21, which gives you 0.476. 0.476. You take that, multiply it by 100 to convert it to a percentage, and now you got 47.6%. So it's almost a 10% chance that you're going to pull two red marbles, right? But it's a 47.6, almost 50% chance, right? You're almost half as likely to pull a red and a blue. All right? So again, probability tree diagrams, you get to see the picture. It shows you the picture. You see all the probabilities, right? They're written up here. You get it like, and then you see the outcomes because they're at the ends of the branches. And you see how you got to the outcomes. You went from red to red, that's red to red. You went from red to blue, that's red to blue. You went from blue to red, that's blue to red. You went from blue to blue, that's blue to blue. So, if the diagram, the tree diagram wasn't here, and we just straight went like this, you could do it like that, write the outcomes and then figure out the probability, but you'd have more to try to think about and visualize in your own head anyway. It's nice to have a tree diagram because then you can see a picture. Right? Like they say, a picture's worth 1,000 words. And a lot of times pictures let you see conceptually what's really going on. So trust the tree diagram. I rock with them. I rock with the tree diagrams. I definitely do. I rock with tree diagrams, But get some practice on problems like this. Definitely get some practice on problems like this so you can master the skill. Remember, setting up the tree diagram without replacement. Some of the problems, there is replacement. This was an example where there's not replacement. And I got a feeling a lot of y'all watching this need to practice these problems because you notice how the probabilities change if there's no replacement. All right? Write your outcomes. You should have an outcome column and you should have a probability column. Also, as a way to check your work, make sure all your individual probabilities add up to 1. All these 1, 2, 3, 4, make sure they add up to 1, meaning the fraction that they add up to is equivalent to 1. Our fraction that we got was 21/21, which is 21 over 21. Another rule in math, or a little cheat code, if you will, is that anytime you got a fraction and your numerator is the same as your denominator, that fraction is equal to 1. Whether it's 10 over 10, 100 over 100, a billion over a billion, 5 over 5, -8 over -8, it don't make a difference. They add up to 1, that means you did something correctly. If you ever add up all your probabilities and it doesn't add up to 1, then you did something wrong. You got to find your mistake. All right. So anyway, ask your teacher, ask your professor, ask whoever for some practice problems so you can master this. You want to master this. All right. Or just go online and do some research. Look up probability tree diagram problems. All right. And shout out to Asada Shakur. Peace.